Okay, so at this step we're going to use the N-evap, or nitrogen evaporator, to evaporate the acetone, and it should leave us with just an oily residue, which is our lipid. So there's a little spring here. What you want to do is just pull a little on the spring and let the flask go, the tube go in. There is some warm water underneath. Okay, so the heat will help the evaporation. Okay. Then you have a little capillary here that you want to insert into the tube. Okay. And you want to turn the little valve here to open it. Okay. Now what's important is that you see some movement into the acetone, but you don't want to have a splash going on, because you don't want to splash all over the equipment or the fume hood and contaminate everything with radiation. Okay, so right here we have a nice flow, and you can see the white formation here, which is the lipid that is starting to form as the acetone evaporates. So after complete evaporation of the acetone, we get a white, oily residue like that. So now we'll talk a bit about C14 and how to work with it safely. The first thing that you should know about C14, it's not something that is very dangerous. It is medium emitting beta particle. So it does not have the capacity of penetrating paper, skin, lab coats, stuff like that. So the only way that you can harm yourself is if you ingest it or if you get it into your eyes. So wearing the safety glasses is a must in this lab. So when you walk into the lab, the first thing that you will notice is the white paper and the yellow radioactive tape. Okay. You assume that this area is contaminated. Okay. So your lab books, lab manuals, pens, any of your personal stuff does not go onto this mat. You leave that in the cold area. I've laid these down here just to demonstrate that in order to minimize contamination to the white paper when you're working, once you're done, anything that has touched radioactive material, you can just lay it down on a Kleenex. Okay, the radioactivity will not go through the Kleenex, therefore you will minimize the contamination to the white mat. Minimizing this contamination also minimizes contamination to yourself. Okay, there's a few things that you should never do when working with radioactivity, is to be working over the floor with radioactive material. So I want to make sure that I'm always working over the mat. If I drop it, then this absorbent paper will contain the spill. Okay, it's very easy to deal with. If you're working over the floor, it falls onto the floor, then we have a problem. The other things that you want to do is maintain a safe distance from the mat. Again, we assume that this is contaminated, so if our lab coat is touching it, then we contaminate our lab coat. Another thing that you want to avoid is to lay your arms down onto the mat like that. Yeah, so now we're going to talk about waste management. First thing you need to know is during your lab, any solid waste you throw into the sharp objects. Okay. The Kleenexes that you're going to use, your gloves, everything that is solid goes in here. And at the end of the day, when you're finished, you find the appropriate garbage and pour it into there. Okay. The other thing you need to know is the liquid waste. Everything you have in tubes, those tubes here, you will pour into a waste bottle in the fume hood. But this one here, what you have in this flask is highly radioactive. Okay? Your source is in there. So that's the most radioactive flask that you have for this experiment. So for this one, you just leave those at your bench, and we'll take care of it. We'll dispose them in the appropriate manner. So now that we have thrown away our liquids into the waste bottle in the fume hood, we need to put the tubes away. Okay, this is just soapy water. Okay, but what's really important is that you make sure that the tube is fully submerged. This is going to stay there overnight and it will be cleaned tomorrow. C14 glucose is soluble in water, so soapy water will clean the tubes and get rid of any radioactive traces on the tubes. So there's one instrument that you touch throughout the lab all the time is the pipette. Other people after you will be using this pipette, so what we ask of you is to just give it a good rinse, just to remove any trace of radioactivity that you might find on the pipette. Okay. So just rinse it thoroughly. Of course you do that with clean gloves, very important. And then you just wipe it and return it back to the bench. At the end of the lab, we will monitor the contamination of C14 across the lab and on yourself, your lab coats, your shoes. And the way to do that, we use wipe test. Okay? What's very important with the wipe test is to make sure that you're working with something that is already clean. So as you see here, everything that I'll be working with for the wipe test is away from the known radioactive area. If my paper is already contaminated, of course, we're going to see a reading in the scintillation counter. Very important, clean gloves, change your gloves just before you're going to do the wipe test. Again, contamination from the gloves can be transferred to the paper and we'll see it on the machine. So what you want to do is you take a filter paper, okay, wet it, and wipe the area that you're testing. Okay. Put the paper in a scintillation vial and then add some scintillation cocktail to the vial. Okay, so here we have the rack that goes into the scintillation counter. This is what your samples are going to be in. Okay. What you have to notice is you have numbers here that go from 1 to 18. Now at the end of this lab you should have 15 samples. Okay? And you should follow the lab manual. If they're in the same sequence as the lab manual, then you can go back to the manual when you're writing your report. Because the only thing you will see on your results are number. Sample number 1, sample number 2, sample number 3, and so on and so forth. The only thing that you need to notice is the user number. It's the only thing that identifies your samples. There are no names, there are no group numbers. The only thing that we will know is the user number. So when you leave the lab, make sure you know which number you've worked with. It's not always in accordance to your group number. So what we have here is the scintillation cocktail. So what it does, it's a cocktail that contains fluors. Okay, so when the beta particle hits one molecule of fluor, the fluor gets excited, and then when it relaxes, it releases a photon. Okay, so one beta particle will hit many fluors on its path, okay, resulting in a flash of light. Okay. The flash intensity corresponds to the energy of the particle. Okay, so that's why it's important to have this cocktail in each of your samples, because without it, we can't detect anything. Okay, so it's already going to be set up at 2.5 milliliters. So all you need to do is take your vial and just slowly pump 2.5 milliliters. Very important that you have that in each of your samples. Okay, so this is the scintillation counter. It can detect gamma radiation or beta radiation, which are electrons coming from the nucleus. In this experiment, we are working with beta radiation. The vial enters a chamber surrounded with phototubes. The light emitted by the flash is captured by the phototubes and an electric signal is produced. The phototube chamber is isolated with lead to avoid the detection of radiation from the outside. So what this instrument does is it measures the intensity of the light flashes that we talked about earlier with the scintillation cocktail. And with this intensity, it can detect which isotope is present. So when when the energy is weak, it is tritium, medium energy is C14, and high energy is P32. It also measures the number of flashes. Okay, that number of flashes is an estimate of the number of particles, so the DPM, that are released by the samples. Okay, all the DPMs are not detected by the instrument, so the instrument has to be calibrated. So from the count measured by the tubes, it can calculate the particles released by the samples, so the DPMs. So here we have an example of a result sheet, and we can see the CPM, so the counts per minute. Okay, and then we can see here that the machine calculated the DPM, so disintegrations per minute, which is the amount of particles released by the sample.